Good morning. Welcome. The new week of calculus. Good morning. Good morning. Thank you for using chat box, Lara. Brian. I see more students. Okay, let's start. I hope everybody is well and good and ready to learn new things. Yes, please confirm. I hope you have your, yes, thank you. I hope you have your tea or coffee. Yeah, and we will start nice, because when we start the day really nice, and actually when the morning is productive, then the whole day is productive. I believe so. And I hope you still, yes, really appreciate the small steps, yes, to be consistent. Because when we are consistent, unfortunately, we don't see sometimes, most of the times, we don't see the result right away. Yes, like day by day. But then after a week, 2 weeks, 1 month, 1 semester, we like developed, we grow a lot. Okay, that's me. Please remember to be consistent, working every day a little bit. Okay, that's what we will do this week. This week we will calculate. That's when we will have like a nice math class. Because we will take all of the limits laws that you learn in the previous week. I was gonna say section 2.3 was the basic limits laws properties. And also you reviewed last week section 2.4 continuity. That's when we know when function is continuous, then the limit and the value is the same, which we still know the difference. Yes, we know the difference, the meaning, the meaning behind the value and behind the limit notation. And now we will take everything and try to compute some limits, which will be a little bit more complicated because most of the functions will create indeterminate form. Okay, we have 7 of them. We definitely know one of them. Okay, that's we will focus today. And then because the sections for this week is 2.5, 2.6, 2.7, 2.8. That means we will finalize chapter 2. 2.5 and then 2.6 you can check a really quick video, because it's just one formula. It's a limit with trigonometric function. Okay, but you can check the video. I can actually write down the limit, but we still have to know how to like navigate. That means 2.5, yes, 2.6 is actually limit like this. Limit as x goes to 0 is a trigonometric form, sine of x over x. Okay, that means actually the whole section is about this. I think on the video I am proving this formula and then I'm applying. That means you can watch after the session or you can watch later. And also 2.7, we will talk about the limits at infinity. Okay, limits at infinity. That means this will be tomorrow. Limits actually as x goes on and on and on. Yes, limits at infinity. Okay, we will investigate this. That means this will be tomorrow. And 2.8 is the intermediate value theorem. Okay, intermediate value theorem. It's also, I don't want to say just, but it's a theorem. You can watch, yes, you can watch the video. And that means for this one, you will watch the video. And for this section. And 2.5 and 2.7, we will cover live. But also what I will do tomorrow, covering section 2.7, we will also have maybe for the half of the time, like a review of all of the limits. Okay, that means it will be quite good review session before the midterm. We still have 2 weeks to take the midterm. Okay, that means covering these limits, we will finalize and I will have like the review. Yes, good questions. That means be ready. I mean, today, tomorrow, every time we have to be ready. Okay, that means that's the plan. Okay. Yes, 2.5, that means this and this one is live. Okay, Yeah, you can, and you know where to find my YouTube videos. Yes, the link is posted on the front or home page, like I think in the middle. Okay, that's mean intermediate forms. We have 7 of them. And can you tell me one of them that we've already learned that form? Who can tell me which form is called indeterminate? Not, I was thinking about the intermediate value theorem. Indeterminate. Oh, okay. That's you know even more because yeah, actually, section 2.7 will talk a little bit about this. Yes, that's one of them. But I was thinking about this one. Of course, 0 over 0. I'm just thinking, yeah, we will focus mainly because yeah, infinity over infinity is another one, but we will, yes, we will talk more about that one tomorrow. Okay, that means 0 over 0. And we know if we have this situation, we know what this means. Yes, we know the meaning. Do we know the answer right away? What is 0 over 0? Hmm? I'm sorry, I can't, yes, express. We cannot really say undefined. That's the thing. It's definitely called indeterminate form at the moment, but we may try to determine the answer, right? That's why we cannot leave the answer like DNA. It could be, it could lead to like completely undefined form, but we have to have proof, yes? We remember, we always, when we end up with the answer D and E does not exist, then we have to have proof. Maybe the one-sided limits are different, maybe some oscillation, maybe some infinity, yeah, infinite limit. Then we can also call D and E. We have to have proof. But the funny thing is, we may have this answer, this form can lead to the finite number. Yeah? Our instantaneous rate of change, like zero distance, zero time. And we actually driving like 50 miles per hour or even faster. Yeah, that means 0 over 0, because when we see 0 over 0, we have to think right away that is not exactly 0. Yeah? It's a really, it's an arbitrary small number. Okay, it's a tiny number. It's not, yeah, it's 0.0001. On the number line, we have a point that has 0 distance to 0, but it's not 0. That's the number. Okay, that's it. Let's see all of them. That's all of the indeterminate forms. 0 over 0, our good friend. Infinity over infinity is another one. That means if one function goes on and another function goes on and on, we have to figure out maybe which one is like faster. Yes, we have to think about this will be called relative rates of growth. Which function is growing faster? Yeah, could be negative infinity also, but like which function goes faster, like to the negative infinity? The same. We cannot say undefined. We cannot really say one unless we know that they are identical. Yes, like that pace, that speed is the same like the other function, the numerator and denominator, then we can say, but we cannot, because sometimes, yes, sometimes we can cancel out and we can say one. No. Infinity is not really a finite number. Yeah, that's, please be really careful. Also, we have, that means these two, okay, these two are quite important. And we will talk more, I mean, all of them are important, but we will talk a little bit more in section 4.5 because we will have a special rule. Today, we will just use algebra. Yeah, we will just use algebra today and tomorrow to actually figure out if the indeterminate form is defined or not. But we still have more complicated models, functions, ratios that we will need more tools. And that tool is, yeah, we will cover in chapter 4. Okay. And then we also have 0 times infinity. We have infinity minus infinity. And then we have 3 power forms. We will not talk about the power forms also. We will leave them to the section 4.5. Yeah. But these 4, actually, I can maybe remove this. These four, I think we can manage without the calculus. We can manage with just algebra, okay? Okay, that's when we understand this one. This one, zero times infinity also, because infinity is not really defined number. That's mean, please, for now, just remember this is also indeterminate. Could be zero, could be infinity, but the funny thing is, could be even a finite number. Okay, it's negative. Yes, yes, Nathan, that's good question. All, yes, all of them. I mean, all of them can have positive, negative. Actually, we have to be careful with the difference. That means, yes, if we have plus or minus, it's still indeterminate because function can grow in the positive direction or negative, like can go down. But now the thing is, what about infinity plus infinity? Big number plus big number. Is this really indeterminate? What is big number plus another big number? Yeah, of course, it's still a big number. Yeah, that's when we see just the addition, no problem at all. Or when we see multiplication, what about big number times big number? Yes, it's a big number. Of course, because I don't really want to say infinity because we theoretically we are not allowed to do the arithmetic on infinity. Infinity, we don't know what it is. But when we know that this is positive infinity plus another positive infinity, it's still infinity. Because when I perform addition, multiplication, then we still have division, we still have subtraction, then we can keep going. That's, we have to be careful. But this is, yeah, that's definitely correct. And we don't have to do any like complicated stuff. We can just say, but we have to be careful because when we have infinity plus negative infinity, this arithmetically, it's this. That's mean then we have to hold on because subtraction is a problem. At them, I mean problem. Easy to solve. We like problems. Yeah. And the same division, yes, the same division. When we dividing, we have to, yes, we cannot really say infinity over infinity, but the negative, yeah, the negative is negative positive is the same indeterminate, but we will then like incorporate this signs, the arithmetic. Like for instance, when we will take negative big number times positive big number, what will be the answer? This is okay. Or the same positive times negative. Yeah. It'd be like positive times negative is negative, negative. Yeah? Or if we will take negative big number times negative big number. Big number times big number is a big number, but negative times negative will give me positive. Yeah, that means this is, yeah, that's it. It's still not a problem. The problem is a difference and the quotient. Okay, and also, yes, zero times infinity. Zero times infinity is also indeterminate because we will learn this later, but maybe I can show you one thing. Before like doing anything, that form must be rewrite in terms of the quotient. Yeah, because looking at zero, I mean, looking at the product, we don't know exactly how to deal. That's the reason that I said that these two are super important because they are relatively easy. All of the forms, even this one, even this one, even those, we will try to rewrite in terms of the quotient. And let's actually look at the product, how easy it is to change product for the quotient. Because multiplying is basically dividing by the reciprocals. That's we may leave infinity, one of the, because this will be a function and this will be a function. That in one function we can leave it on the top and the other we can flip it. Yes, infinity dividing by 1 over 0 is still infinity times 0. Yes? And now let's look at this funny thing. What is 1 over small number? Do we remember from last week? 1 over small. I hope, yes, I hope you watched the basic. Yes, 1 over small is actually big. Small for us, because we are super professional mathematicians, small number is 0, big number is infinity. That means 1 over small is big, 1 over small is big. We still have to know if it's the right-hand side or the left-hand side of 0, because then will be respectively negative infinity. And we can see that we manage, do you see that funny thing? The product we rewrite in terms of the quotient, and it's one of them, always will be. And then later you will see the difference. Or let's see the other way. Maybe we can decide that we will leave there's the function that goes to 0 on the top, and we will flip infinity. The same, yes? 0 divided by 1 over infinity is 0 times infinity. Yes, everything is really, really like informal, yes, really symbolic, because dividing by 0. And what is 1 over big number? Do we know what is 1 over big number? Of course, it's small. Yeah, really informal. That means small is 0. And the same, we managed to rewrite that product in terms of the quotient. This is one of the way. Yeah, just the arithmetic. Okay, but 7 indeterminate forms. Let's focus on these. Actually, let's focus on at the first one, 0 over 0, because that's instantaneous rate of change, instantaneous velocity. Okay, this is from section 2.4, really important property. If a function is continuous function, we know what continuity means. Yeah, this is actually, continuity is kind of this. If the limit is the same like the value, then at the number a, yes, at the number a, which is in the domain, because if the function is continuous everywhere, then a is in the domain, we will have this property. Okay, we can see that. Means when we calculating limit of the function as x goes to a, basically is just the value. But as I said, this left-hand side and the right-hand side of this equation we know the difference. That means the question that we did in the previous section was parabola x squared. And what is the limit? I don't know, remember if it was 3 or 4. What is the limit as x approaches 3? Limit as x approaches 3 of the function x squared. Can you tell me? What is the limit? Of course, it's just, and we can see, I can basically use this direct substitution, because parabola x squared is continuous everywhere, and especially at 3. X equals to 3 is in the domain. Yes? Then we substituting, and it is 9. But what about the value? What is the value, exactly the value, f of 3? Yes, it's the same thing. Actually, I can put, okay, let me just, it is 9. But let's maybe make it one of them blue. That means this one is exactly, yes, exactly 9. But limit, yes, limit function is approaching, because x approaches 3. As x approaches 3, the function is approaching level 9. That means that red line and the blue line, it is the same, but we know the small, yes, the deepest meaning. Okay, but we will use a lot. If function, yes, if we remember this from section 2.3. If function is continuous function, at that number a, we can just substitute. Okay, and this is the limit. We don't have to go through this approximation. Okay. Okay, but for instance, question like this. Evaluate the limit. That means let's deal a little bit with nice algebra. You can have your pencil, your notebook, and let's start. Find the limit as x approaches 1 of the function x squared minus 1 over the quantity x minus 1. And we may see x equals to 1 is not in the domain. Doesn't matter. That means we do not have value. This function doesn't have value at 1. It will be probably open dot, or maybe different type of, or maybe jump discontinuity, or maybe infinite discontinuity. Okay, that's what we can do. Yes, that will be the good step. But actually, I was supposed to ask you one extra question. if we actually perform the direct substitution, because that's what we have to do, we are not allowed to use 1 directly at the moment because 1 is not in the domain, but we will do it to have some information. When we actually take 1, what we getting when we substitute 1 to this function? Yes, we actually getting this indeterminate form. 1 squared minus 1, 1 minus 1, we are getting 0 over 0. Then let's say we like this because we will kind of know what to do. First of all, we freeze for a second, because please, yeah, on the test or like whenever you will see the limit, do not circle the answer 0, because 0 over 0 could be 0, but most likely it's not. Yes? Could be, I can show you an example, could be anything. Yes, this could be 0, could be big number, could be negative big number, or could be just a finite number. Let's say L, finite number. Okay, that's what we will do, 0 over 0. Then we have to think that function on the top and function at the bottom has common factor at that 1. Yes, common factor at 1 means that x minus 1, because 1 is the 0. When we substitute 1, we're getting 0. That means x minus 1 is a common factor. We have to find out this common factor. We have to find out that common 0 and then cancel out. But we have to see the formula. We cannot just cancel out this. No, because it could be hidden, could be 0 times another quantities. We have to have exactly the common factor. Okay, that means this will be the procedure. Yes, we will factor out, we will find this common factor, and then we will cancel out. After canceling out that zeros, most likely we will substitute the x, because the new simplified form will be defined at 1 or at any other number. Okay, that's how we can factor out. Let's come back. Quadratic, because x minus 1 is the linear, is the simplest form. X squared minus 1, can you help me to factor out? X squared minus 1. Who can help me? Because I think I typed. Did I type this? Oh no, I think it's x minus 1, x plus 1. Yes. Lara, if this will be x squared minus x, then we can factor out x. That will be correct. But we have x squared minus 1. Yeah, I know it's yeah. Okay. And now do we see the common 0? Of course, we see the common 0. Let's cancel out. That means this will be the way. Yes, a little bit of algebra. We will cancel out. That means this, I'm canceling out 0 over 0. And we just end up with the simple linear function, x plus 1. X plus 1 is defined at 1. Yeah? Then we can use direct substitution. And the final answer is 2. Okay, but we still have to know this is limit. Okay, this is limit for this function. Let me have, okay, actually I have a room. Original function was x squared minus 1 over x minus 1. It's not defined at 1. We do not have the value. That means that 2 is not the value. We did simplify. Let's put nicely. We simplify to this function. That means this one is not defined at 1. And this one is also, this one is also not defined at 1 if we would like to draw this function. But for the limit purpose, we can substitute, because the expression algebraically is defined at 1. It's 2. That's me how this looks like. We can draw a line, x plus 1. I think looks like this. Correct. But at 2, not at 2, at 1, the limit is 2. Let me put at 1, it's a removable discontinuity. Okay, it's removed. It's at the level 2, the limit is 2, but no value, it's open. That means it's a line with a hole. Okay? Of course, it's supposed to be small, nice hole, but I'm making like really pronounced. Okay, that means please, please, understand that too. It's not a value, it's actually, but how we can get that too? Through the calculation, we directly substituting. That means this direct substitution that we actually using, it's just the tool. It's just the tool to, because if we will try to substitute numbers relatively close to 1, 0.9, 0.999, 0.999, even more nines, or on the right-hand side, 1.01, 1.00001, and then approximate, we will end up with 2. Yes? That we don't have to. We know that that expression is defined at 1. We can substitute. But always think what we're doing is just the tool. It's just the mathematical property, the tool. Okay, that's me now. Yes, we cancel out, then becomes a whole. Always. When you cancel out that 0, it's still there, right? I mean, it's still like this. We still have no value. We still have no value. That means we may say that these two functions are equivalent if we indicate this. If without saying, especially for the second function, this one, without saying that x is not 1, these two functions are not equivalent. Because this is line, beautiful line, no problem. But we know that this line came from that fraction, and this is not defined. But yes, when you cancel out, we will have always removable discontinuity. If we cannot cancel out that 0, it's probably infinite discontinuity. Okay. But let's keep working. Okay, I list couple of special formulas. Yeah, the special product formulas. We actually use the first one. Maybe sometimes we have to expand. Depends what we algebraically. And also, please know number 6 and number 7. Yes, how to factor out cube, even the addition we can factor out. And the foiling is probably easy. Okay, I can leave it this one for you. And let's look at this one really quickly. Let's see, because we can do more complicated. Evaluate the limit. That's how this function behaves at 3. X minus 3 over x squared minus 9. The same situation, similar situation. Oh, no. I wanted to x is not, x equals to 3. It's not in the domain. Yeah? But what we getting when we actually do the direct substitution, we have to perform this direct substitution. Because then we know, because if it's not 0 over 0, then it's another story. It is 0 over 0. Everybody is computing. I hope you're computing. 3 minus 3. 3 squared minus 9, 0. It is 0 over 0. Then the same thing, 0 over 0. We know that we have common factor between these two polynomials. Let's find out, let's cancel out, and see what's happened. Okay, x squared minus 9. We see the common 0. So simple. Now we good. Okay, and what is the limit now? It's just the tool that we directly substituting. The limit is 1 over 6. Thank you. And the same thing, yes, we have to be careful. It's not the value. Value does not exist. That's we did simplify. We simplify, maybe I can just point this function to this one. 1 over x plus 3. It's easy to draw. I hope you check the basic functions. The function 1 over x plus 3 is just the hyperbola. Yes, 1 over x in the first and the third quadrant, but plus 3 means that we're shifting. We're shifting. Actually, it's okay. It's interesting. Okay, it's interesting. Let me, because this will be also, we will need this, yes, tomorrow or this week, basically. When we look at the original function, actually, what was another number that is not in the domain? Because let's see the difference. Another number that is not in the domain. If I will ask to compute the limit as x approaches -3. Let me copy maybe function. And now, what is happening? What is happening when we do the direct substitution? Okay, because this is actually, okay, this is limit that we're supposed to be able to compute. It's a good, yes, good limit. What happened when we directly substituting? Because that's what we can, even if it's not in the domain, the first step is always directly substituting. We're getting, this is still 9, because -3 squared is 9. That's we're getting a constant, like a finite number over 0. Is this indeterminate form? Oh, yes. Let's come back really quickly. That's indeterminate forms. Do you see a constant number over 0? Do you see, like, let's say constant over 0? Do we see that this is, yeah, we just have 7 of those. Constant over 0 is not, constant over 0 is actually not really an indeterminate form. But let's look at this one. Yeah, oh no, I can maybe, I can rewrite as a constant times 1 over 0. Do you see on that screen 1 over 0? Do you see 1 over small situation? It's actually this. 1 over small number is a big number. And that means this is big. 1 over small is big. And times constant. It's still a big number. Only positive, negative, only the arithmetic we have to, the algebra, we have to like remember to adjust. If this constant is positive, negative, or if this is positive, negative, big number. But please, yeah, constant over 0 is not indeterminate. It's actually, we see right away, it's the same like 1 over small number is a big number. When we have 0 in the denominator, not 0 on the top, then it's just dividing by small number. Dividing by small number means it's big. Yeah, dividing by big number is a small. Okay, that means this is actually, this will be big. Big is infinity. Let's get that answer. That's actually good. We have room. Okay. And then we can, yes, then we can draw it because that will be nice. This is definitely good. Let me do this. Okay, that means and I can rewrite as a -6 times over, times 1 over 0. Yeah, we have negative, that's why we have to be careful. 1 over small, but now the thing is 1 over small, we have to make sure that that small is positive or negative. This is actually good limit. We have to know, let me, no, I don't wanna, that's me what I will do, because we don't know if we did substitute -3 exactly, then it's exactly 0. But we know that this is just the tool. We know that it's just a number close to -3 on the left, on the right, or on the left. That's we will investigate the right-hand side. Okay, that's when we will take the number -3 from the right-hand side and do the direct substitution. This will be not 9. It will be a little bit more or a little bit less. Please help me. I can maybe draw a number line really quickly. -3, and we need the number on the right. This is left, this is the right-hand side. What is the number on the right-hand side? Okay, let's check. I think -2.999. That means this will be a little bit less. Yeah, this will be not 9. It will be like 8.99 will be less because this is less. Correct? That means this will be 8.99 minus 9. It's still a small number, yes, 0.0001. But this difference, it's positive or negative because that's the moment. 8.99999 minus 9. It's actually negative. That means I can indicate, because for the 0, negative, positive, left and the right-hand side, I can put the indication left or the right. That means this is negative. 1 over small negative number is negative infinity, negative big number. And now negative times negative is positive. Times 6 doesn't change. That means this actually limit is negative, is positive infinity. If the limit is infinity, we have a vertical asymptote and function goes up to the positive infinity on the right-hand side at -3. And as we can see, different situation. Let me maybe, this is indeterminate form, and this one is not. Let's use the green. This one is not. Both of the number, 3 and -3, are not in the domain. That's when we do have this continuity, but different type. For 0 over 0, we get a finite number. That means that this is the whole, because we cancel out that 0. We manage to cancel out that 0 from the denominator. This one, we will not cancel out. We can see x plus 3 stays in the denominator. Okay, that means now we have all of the information to draw a function. I mean, we can also use, okay, that means now this function x plus 3 came from this one, and then we have 3 and we have -3. Okay? Because that's also sometimes the common mistake when we see these denominators, and the question will be, please find a vertical asymptote. Yes, you will see the zeros, okay, 3 and -3, and we will list no, because one of them could be removable, which this happened at 3. I can actually remove this, because limit at 3 is 1/6. Let me draw a function, because I know that function looks like this. It's just shifted, yes? Like if this will be just algebra class, it's just shifted to the -3 units to the left-hand side. But at 3, we have a whole, and that whole is 1/6. Because this function came from, yes, the top one, the original one. And actually, we can see, we calculate that limit on the right-hand side, function goes up, yes, to the positive infinity. Okay. This is nice hyperbola, but we do have a whole. Yes, it's no value. Vertical asymptote at -3, but removable discontinuity at 3. Okay, nice, yeah, nice function. Okay, let's keep working. That we not only have algebra, we have, but please know what are the indeterminate forms, and also know 1 over small, 1 over big, and then we know the answer. This limit is quite nice. Okay, I have another one. It's 0 over 0. You can find the common factor. You can cancel out, and it will be a finite number. Okay, I have another one. 0 over 0. You can find the common factor. You can cancel out, and it will be a finite number. Okay, this one, it's 0 over 0. We have to find the common factor, but this one includes the square root. Yeah, it's not like a polynomials that we just have it. We still have to find a common factor. That's what we will do for the square root expression, like how we can factor out, because we don't really see the polynomial like a greater degree than 1. And for, like the square roots, if we will see the square root expression, what we will do, we will multiply and divide. That this means that I will multiply the numerator and denominator. Yeah, it's kind of like rationalizing, but in this situation, we will not rationalize denominator, usually what we do, because we never leave the square roots in the denominator. Yes, it's the same situation. That's mean Brian, or I mean everybody, what we will do to rationalize the expression. We have to rationalize the numerator. We will multiply by what kind of expression? Conjugate? Do we know the conjugate expression? The conjugate expression is when I take A minus B, and then the conjugate, this is expression, and the conjugate means that it's the same A, the same B, the same first and the second quantity, but opposite. Yes, we will change the sign. That's what we call that these are the conjugate expression, A minus B, and then the conjugate is A plus B, or the other way, the signs. And yes, we will multiply, and the expression, the conjugate, not for the denominator, for the square root, always including the square root, because actually what this is equal to when we FOIL really quickly, A minus B, A plus B. The first quantity squared, the second quantity squared, minus A squared minus B squared, yes? Please know, when we have conjugate, that's the quick. So what we will do, we will definitely FOIL, we will definitely multiply that conjugate, because we may simplify. We can see square root of x is the A expression. 5 is a B expression. What is square root of x squared? Square root of x squared. It's just x. I mean, we still have to be careful, because if it's too general, we have to put absolute value. Yes, we remember, because if x is negative, but since we are close to 25, left and the right hand side, it's positive. That means, yes, we may just say square root of x squared is just x. Okay, that we can see, we will simplify. Let's remove all of that algebra. And now let's see. Okay, that means square root of x squared is x, 5 squared is 25. And you may probably notice I didn't multiply, I didn't distribute denominator. Right? Because why I didn't do this? Do you see this? If we will FOIL, if we will distribute everything in the denominator, we will be not able, yes, we will be not able to cancel out that factor, which actually is 0. And use the blue color. That x minus 25, it will like melt out in the expression. We will be not able to see that 0. And again, that common factor that we really want. But now we see that common factor. After that conjugate, we managed to find out. Okay? Yeah. And then we have just this function. Now we able to use the direct substitution. What's the final answer? Who can help me? 1 over 10, 5 plus 5, 10. Oh, yes, thank you. Okay. And the same, 1 over 10 means that it's a whole at x 25. Yes? We do not have function, doesn't have a value, it's just the whole. Okay, we will skip the drawing. Similar, actually, similar, because function 1 over square root of x plus 5, it's also, yes, similar to. Okay, but please remember this, the message on this example is when we see the square root expression, use the conjugate. Okay. Yeah, let's keep moving. This one, it's 0 over 0. You can just expand, you can cancel out, you will see nicely, common factor, and you will cancel out. The same for this one. This one is squared, this one is cube, okay? And this one, the same. You can just simplify the fractions, maybe common factor, maybe rewriting as a one fraction, like one, everything supposed to be placed above and below one fraction bar, easy. Oh, but do I don't have a room. I wanted to, okay, let's keep going, because I would like to, I mean, okay, let's see. Let's keep working. I wanted to show you that 0 over 0 can be actually 0, but what is the case? 1 second. Okay, what about this example? And we remember, yes, we have to always review the lecture notes, yes, because I always include everything. It's literally everything. Okay, tangent of x over secant of x as x goes to pi over 2. Wow, doesn't look good. Did I type? I didn't type. Good. Oh, blue. No, let's use red. Red is a nice color for learning. Okay, limit and then tangent of x over secant of x. Actually, what is tangent of x at pi over 2? Oh, that's interesting. How tangent? Okay. We can actually do this, but I wanted to, okay, because we can, okay, let's investigate. We may look at the graph, but let's do like algebraic, it's not algebraic function, but we may use the property. Yes, I can put sine of x. That's actually correct, Lara, that's correct. And then let's substitute maybe pi over 2, direct substitution. I'm just doing my first step, direct substitution. Okay, and what's the value of sine at pi over 2? Sine at pi over 2 is 1, yes, and cosine at pi over 2? It is 0. That's and what is 1 over small number? 1, yes, it's a big number, but we still don't know if it's plus or minus, actually plus or minus. Okay, but because then we have to investigate left and the right-hand side. But it's definitely infinity, yes? Plus or minus, we don't know. Okay, that means I can say plus or minus infinity. And then what about secant? Secant is 1 over cosine, the same thing. 1 over cosine and 1 over 0, 1 over small is a big, the same, we don't know. We have to investigate. That means actually, because we may rewrite and you will rewrite right away, but I just wanted to show you that what we actually getting. Big number over big number. Is this indeterminate form? Yes. Okay, that means I just want to make sure that we recognize this one. Yes. Okay, that's what we can do. We still don't know because we will learn really nice tricks tomorrow about the infinities, but really nice tricks. But infinity over infinity at this situation, we know how to deal with 0 over 0, maybe, or we can find, but even if it's infinity over infinity, we can still try to rewrite this or maybe find something in common. Because infinity, I don't want to say they have common factor because infinity, but they have something in common. That's when we see expression like this, and especially the trigonometric, we can always rewrite. Yes? And one thing is we actually did. We can rewrite in terms of sine and cosine because possibly some of them will be cancelled out. Yeah, that's let me just copy the limit as x goes to pi over 2, and tangent is sine of x over cosine of x. Secant is 1 over cosine. And how this will simplify it? What function we will get? Yes, because we can say sine over cosine dividing by fraction means multiplying by the reciprocal. Limit as x goes to pi over 2. Yeah? And actually we can see this is that 0. Yes, we did cancel out because cosine was the problem at pi over 2. We managed to cancel out. We just have sine over x. And what is the limit at pi over 2 for sine over x? It's just 1. That's this is nice. Oh, it's actually 1. It's okay, but it's a nice example that infinity over infinity leads to the finite number. Yeah? And that's, but always, for the trigonometric, we can always rewrite. Yeah, we didn't even deal with 0 over 0 because sometimes when you rewrite and simplify it, we may still get 0 over 0, but then will be maybe easier to find like another form to cancel out. But yeah, we did simplify it. Okay, let's see what else. This is actually the difference, but let me just absolute value. We can maybe, let's do a little bit because we have, yeah, this one is the difference. Yes. x goes to 1, and we have to find out that limit. However, that's what we see. Yes, what we see. What about the first function when we do the direct substitution? Are we getting this? And actually we're getting this. That means 1 over small is a big. 2 over small is also a big. It's a difference. But I think I have to indicate, because we may have a, let's say, evaluate the function at x equals to 1 on the right-hand side, okay? Because then we can see this is positive, and because that's important. If we will end up negative infinity, for instance, minus infinity, what is this? Is this indeterminate? Big number, negative big number, and then another negative big number is a negative big number. That means we have to be careful. And then one from the right will be a little bit more. This will be also positive. That means yes, this is indeterminate. That means I think I have to say this. Otherwise, we have to check both sides. Probably both sides will be indeterminate, but let's just use the right-hand side. Okay, and what we do, that means this is the example of the difference. What you will do? Do you remember what I said at the beginning when we dealing with the other indeterminate forms, like then the quotient? We still like to see the quotient. That's we have to rewrite. Yes, we have to turn them into the quotient. And we will see, maybe it will be 0 over 0, maybe infinity over infinity, but then we can still, simplify. That means always try to rewrite as a one single fraction. When we have a difference of two fractions, just the common denominator, right? That's almost like self is giving us the instructions. Okay, that means the common denominator, the lowest common denominator. Oh, actually, no. What's the lowest common denominator? I don't have to repeat. This is that fraction, and this one includes x minus 1. Correct? That's a little bit. I can still just multiply these denominators, but let's do the lowest. That means the lowest common denominator is x minus 1 times x plus 1. That means I have to just multiply the first fraction by x plus 1, because x minus 1 is, and this will be 2. Okay, do you think that's right? Just the common denominator. It's okay, this is not together. Limit, and always copy limit. Yes, please, don't. Okay, that's we have x minus 1, x plus 1, and then we have x minus 1. Really nice, really nice. We see, let's use the blue color. We see the common factor. That's the common 0, because x minus 1. Okay, that's what is this limit equals to? You have to give me the correct answer. 1 x plus 1. Now, of course, 1 plus 1, 2, 1/2. It's an interesting. Big number minus big number, finite number. Yes, 1/2. But this is the situation on the right-hand side. You may try to look at the left-hand side, but yes, nice limit. Okay, and then this one, you can do it. It's just 0 over 0. You can expand, cancel out. Common factor will be ready. But what I wanted to do, I think I make it just to, let me maybe add a slide. And then we will carry on with the limits tomorrow. Okay, I just added the slide. Definitely 2.7, the limits at infinity, and then we will have lots of infinity over infinity. But then I will also include nice question. Yes, nice. We know what nice means. Helpful for the assignments and for the tests. Okay, 3 limits before we leave. limit as x goes to 2. And let's say x minus 2, x minus 2. Limit as x goes to 2, x minus 2 over x minus 2. Let's do this way. Okay, and one more. Limit as x goes to 2, x minus 2 over x minus 2. This one, I think I have to indicate the site. Okay, because otherwise will be, let's see. Okay, what is the first limit? Do we know the answer? Or maybe direct substitution. Let's be consistent with our, direct substitution for all of them. What is direct substitution? 0 over 0, 0 over 0, and 0 over 0. Okay, and we will have 3 different answers, that we can see what kind of zeros we have. Because we may notice number 2 kind of like repeats the 0 in the denominator. Number 3 repeats, we have 2 zeros. We will cancel out one of them, but one of them will stay. Okay, the first one, do we see the common 0 right away? I believe so. It's exactly the same thing. Then we have no problem to say this. No problem, because it's identical zero. I am not really canceling that zeros. I'm canceling the exact expressions. Okay, what about this one? This one will lead, we can also cancel out one of the factor, but what happened? 1 over x minus 2. 1 over 0. That means we did cancel out one of the 0, but one of the 0 stays, because we can see we theoretically had this 0 times 0. Of course, we're not writing this way. Yeah, that's the difference. If you notice that we have 2 zeros, one of them will be cancelled, one of them not. Yeah, and what is 1 over small number? We learned today. It's a big number, but please tell me, because we cannot leave it like this. It's positive or negative if 2 is from the right-hand side. That means this will be 2.01. It will give us positive number. Positive, yes. If this will be on the left-hand side, it will be negative. As we can see, nice hyperbola again, on the right-hand side will go up, on the left-hand side at 2 will go down. Okay, and now let's look at this one. I can cancel out that zeros because we have square here. And we end up with x minus 2. X goes to 2. What is this limit? Just 0. Just 0. But please notice, we did cancel out, we did remove the 0 from the denominator. Then we can answer 0 if I can even leave it that squared. Yes, then we can answer 0 if we still end up with 0. But please do not answer 0 if it's still the expression in the denominator. Yes? That factor 0 in the denominator. Okay, 1, the final answer. 1, infinity, and 0. Okay? And all of them were almost the same, 0 over 0. And we can see we have the taste that the function could be different. They could behave different. Okay, thank you very much. And yes, tomorrow will be quite nice session. I mean, every session is nice, but we will have a nice review. It will be nice for the exam. Okay, for the final. I mean, for the midterm and final midterm exam. Yes. Of course, Lara, you can ask any question on the discussion, even if it's from the past week, you can ask this week, yes. Yes, that's good. I don't see it because maybe we're supposed to not ask the question from the current quiz in the current week, but yes, from the past week, you may ask this week. Yeah. Yeah. And if nobody answer, I can try to answer. Okay. Yes. Okay. Okay. Thank you very much. And please join me tomorrow. Thank you for your help. You don't know how much I appreciate your contribution. Yeah. It will, yes. It will be the reward or award. I never know the difference. Okay. Have a nice day and see you tomorrow. Thank you.